Aloha and welcome. In this video, we're going to be talking about insertion sorts. So insertion sorts are kind of like a little bit of what we've seen before. Let's go ahead and take a visual look at it. So when we're looking at, let's say, an array here that has a certain number of numbers in it, we're going to treat this array as partially sorted and partially unsorted. So when we start off, we're going to treat the first element in here as being sorted and the rest of it as being unsorted. So what we're going to do is we're going to start an outer array. It's going to start here at the first element or at the second element, and it's going to at the I equals one element, and it's going to go through to the end of our array. And each time it goes through here, it's going to say, okay, we're starting here. I'm going to take a look at this element right here, and then I'm going to compare this one to the last one. And when I compare it to the last one, if the current one that we're looking at is less than the value for the one before, I'm going to swap these two to put them in order. So the first time you go through here, you look and you see, okay, first time we're looking at this element in the outer array. Then for the inner array, we're going to take a look at here and compare it with the previous. These two are fine the way they are. So we go ahead and we kick out. And then we go to the next iteration of I. So I is going to be 2. We're looking at 15, and then we compare it to the one previous, and they are in order. So then we move to the next one, the next outer iteration. We see it's 20, and with 20, it's greater than 15. So we're still not needing to do any swapping here. And then we get to 32, and 32 likewise is greater than 20. So we're still in order here. So we've gone through this whole thing and not need to do any swapping at all. So the way this works, I'm going to zoom in on here for you. So this is our outer array, right? Our outer loop right here. We're starting with the first element and we're going through to the end of it. So we're starting with I say the first element, the I equals 1, which is technically the second element, and we're going through to the end of it. And we're going to treat this I equals 0, or I actually in this one, it's right here. This is the borderline between the sorted and the non-sorted. So we're treating the first element as already sorted. And then what we're doing is we're starting that inner loop. And the inner loop essentially is going to have J assigned to whatever I is in this loop. So J is always going to start here at our border, and it's going to be looking backwards at the sorted stuff to see where this current number that we have is going to fit into there. So what we're doing here essentially is at each step in the J loop, or the inner loop, we're going to be looking. We're going to say, hey, are these two out of order? If they're out of order, we're going to swap them, and then it's going to go and compare the previous two and swap those as necessary, and then go to the previous members as long as we have members there, which is the J greater than 0. So all the inner loop does is it takes a look, and it takes a look and sees if we need to swap it. If they're out of order, it's going to swap it. Otherwise, it will stop at that point because we know that the rest of it to the right is ordered, or to the left is ordered. So again, let me re-explain this just for the sake of thoroughness. We're doing an outer loop that goes through here from the beginning, the 0th element, or from the first element, the 1th element to the end. And we're going to set up an inner loop as well, setting J equals to I. Wherever we're at in that loop, that's where we're going to start for the inner loop. So when we get that inner loop, it's going to compare this element to every previous one, and it's going to see if it's in order. If it's not, it'll swap those until it gets down to the right place, and then it'll insert it there, but then it'll cut off. So it's best to look at it with an example. So here, okay, they're going with a little bit of a scrambled one. So we're starting out at 1, and this is the border, really. This is considered the border between, the I position is considered the border between sorted and unsorted. Everything over here on the left-hand side, that's going to be considered sorted. This is unsorted. So we start off here at and we set I equals to, or J equals to I. So we're looking at this one right here. And then we start our inner comparison and we say, as long as we haven't hit the end of it, we're going to be comparing the current one to the current one minus one, or the current index minus one. So we look at these, we see that 6 indeed is less than 32, meaning these are out of order. So then when we hit play here, it'll go ahead and swap these and swap these out. So it does a comparison of the two. It checks out that they are out of order. So it's going and it's assigning 6 the temp. So it can do the swap there. So it swaps it. So J hits 0, and that's going to be the end of the while loop. So then we're going to increment I at this point. Well, yeah, it fails out. So it goes to the next position of I, which is 2. So it goes and sets J to that as well, compares the two. We come up with a comparison. Oh, yeah, that's not, that one still needs to be, that one needs sorting. So it swaps the two. Then it goes and it checks. Yeah, it goes to check if the next two are in, proper order. They are not out of order. So the thing to understand is the while loop here, that's checking to see if they're out of order. So what it's really saying is, while we haven't hit the beginning of our array and they are out of order, keep doing this. So as soon as it's in order, which it's going to come back as negative here, false, as soon as it does that, it's going to kick out of our while loop and go to the next outer iteration. Okay, so that's something you need to keep in mind. It's saying while we haven't hit the beginning of the array and the numbers are still out of order, we're going to keep on swapping. So that's what it's doing here. So then it goes to the next index position, which is 3, sets J to it. Then it does the comparisons between the two to see if they're in order. They're not in order here, so it's going to swap them. So it does the swap. Then it goes and back to the next iteration of the inner loop, and it compares the 3 with the 15, and it's obviously incorrect, so it's out of order. So it's going to go ahead and swap them again. So it swaps those. Now it goes to the next iteration, which is comparing 3 and 6. So it's still out of order, so it's going to swap those two. And then J is going to be 0, which will cause it to fail out of the while loop. So then we continue from there. We go to the last element, 20. We set I equal to J. And we're comparing these two elements, J to the one previous. It's out of order, so we go ahead and swap them. Then the next time we go through comparing J, we see that they're not out of order. So at this point, we can stop our search because we know that it's going to be, there's nothing else we need to check. So here is the full algorithm in Java. It's very similar to the code that you saw here. They just add in code over here where it's going to, it's going to show you the unsorted thing. It sets up a list here of numbers, then it goes through it, displays it, and then it goes to the sort and then shows you what it looks like sorted. So here's an explanation of everything that I just talked about, why you're doing what you're doing. And then it's got some questions here that are helpful. So assume insertion sort's goal is to sort in ascending order, meaning you're going from a lower number up to a higher number. Given the list 20, 14, 85, 3, 9, what value would be in the 0th element after the first pass over the outer loop I equals 1? So in I equals 1, you're starting here, and you're doing a comparison with the previous element. So that's 20. You're going to do a flip there, so you're going to have a 14, 20. So the first element should be 14. So you check, and that's correct. So then, given the list 10, 26, 14, 7, you can see these are out of order. What will be the list after completing the second outer loop iteration, I equals 2? So this is I equals 1. This will be the second one right here. So after the first one, you notice that there will be no swaps there. But after the second one, you're going to have to swap the 20 and the 6. So then you'll have the 60 here. Then you'll have to do another one right there. So 6 should be in the bottom. So the list will look like 6, 10, 20, 14.7. So yeah, and you can just continue doing this. So yeah, it's just going to ask you to, run that on paper essentially. So when we're talking about the O notation here, the insertion sort's typical runtime, it's going to be O of n squared. That's because you have that the outer loop, and you've got an inner loop as well. So you're doing the outer loop n minus one times, and then you're doing the internal part, an average of n, over two. So that's going to give you an n minus one times n over two. That gives you O of n squared. So yeah, that's again not very efficient. And there's more efficient algorithms out there that are faster, but they're a little bit more complex. So in here, in the worst case, assuming each comparison takes 1 microsecond, how long will insertion sort algorithm take to sort a list of 10 elements? So let's see, in the worst case, so the worst case scenario, everything is out of order, right? So on the first pass through, we will have one swap that needs to happen. Then on the next time through, it's going to need two swaps. Then on the next time, it's going to need three. So essentially, you're going to have to add up the numbers 1 through 9 because you're going, one swap, two swaps, three swaps. So you've got 10 elements. So you're going to have to do add up 1 through 9. If you add up 1 through 9, that comes out to 45, I believe. Yeah. So you can see here. So anyway, this is like in the previous section. Go ahead and use your own notation to figure out the different or the how many times longer it'll take to do 20 versus 10 elements. Next, we're talking about nearly sorted. Nearly sorted, it's a little bit confusing, but well, it's actually common sense, but the O notation for it may be a little bit confusing. So for sorted or nearly sorted inputs, your sorts runtime is going to be O of n. So a nearly sorted list is it only contains a few elements not in sorted order. So like in the example they give here, you've got 14 out of order. It's nearly sorted, it only has one that's not in the sorted position. So they want you to talk about, or they want you to identify whether or not these are sorted or not sorted. And you can look through them and get an idea like, oh, this is sorted. Then you look through here and you see, oh, 19 shouldn't be there, but that's really the only one, so that's almost sorted. So you can go through here, and I'll leave the third one for you to do. But now we get into the O notation part of it. So for each outer loop, that you execute, the element, if the element's already in sorted position, you only have a single comparison that's going to be made, right? So the first time through, or for when you do it, if you are in sorted order, you're going to do that comparison. You're going to find that you're greater than the element right before it. So that's the only comparison you need to make. So your best case scenario there, well, the sorted position, having them sorted like that is going to be the best case. So it's only going to take one comparison. So yeah, so it says each element not in sorted position requires at most n comparisons. So that's correct. So each time you go through there and you don't have it, let's say worst case scenario, you've got a number that's lower than everything else. So you're going to have to do n number of comparisons as you go through there. So if you've got a constant number C of unsorted ones, sorting the n minus C sorted elements requires one comparison each, and sorting the C unsorted elements requires at most n comparisons each. So the runtime for that is going to look it's going to be O of n minus C times 1 plus C times n, and that's going to give you O of n. So we'll be talking more about algorithms and the costs and everything in the next chapter. But just have a general idea of why this bubble sort has in a nearly sorted situation, it's O of n. So next, we're looking at the participation activity. It's going to we're going to look at using insertion sort for a nearly sorted list. It's pretty simple. If you start out, with the first element there, you're going to go to the 7. You're going to do the comparison. You're going to see that they're in order. Then the next iteration, you're going to go through. So you notice that every time we go through here, we're making exactly one O of 1 comparisons. So it's this last one where all of a sudden you get to the worst case scenario where it could be, well, this one isn't a worst case scenario, but what's going to happen is you have to make up to n comparisons to get to the proper space. So now we're looking at participation here, insertion sort algorithm execution for nearly sorted output. So we're given a list of 10, 11, 12, 13, 14, 15. How many comparisons will be made during the third outer loop? So if I is 3, so if we're going to start like I is 1, I is 2, I is 3. So if we are, let's see, how many comparisons are we going to have to make at I of 3 right here? So we look over here and we compare it to the one before it. It's less than, so we're in order. So we're just going to do 1. So given the list 10, 11, 12, 13, 14, 7, you can see here that we've got 7 out of order there. How many comparisons will be made during the final outer loop? So that's 5. So we have, this is 1, 2, 3, 4, 5. So the last one, we're going to be doing a comparison here. Then we'll do a comparison there. So that's 2. Then 3, then 4, and because it's less than 10, it's going to be 5. So it'll be 5 total there. So then given a list of 18, 23, 34, 75, 3, how many total comparisons will, yeah, so I'll let you do this one on your own. Try that one out. So insertion sorts, okay, go ahead and start this. Given a list of 33, 34, 44, 48, 50, 43, 24, when using insertion sort, what is the value of I when the first swap executes? Okay, so we're going to start out here when I is 1 and there's nothing to swap. Then this one, when I is 2, there's still nothing to swap. Then when I have 3, there's nothing to swap. I have 4, nothing to swap. I have 5, so it's going to be on 5. So it's going to have a series of things like this for you to do. Go ahead and check through there and hit next, next, next till you're finished. And that is it. So insertion sort, just keep in mind that what it's doing is it takes your array into an unsorted and sorted part, and it's going to start at the border for it, the I equals whatever. It's going to then take that element and it'll loop on your inner loop through that, comparing it to the previous element and doing a swap if necessary, all the way down to the j equals 0, or to the first element, essentially, swapping the two as necessary. So do note that. Note that in a worst case scenario, you're talking about O of n squared. In a nearly sorted list, you're talking about O of n. So if you have any questions, feel free to reach out, ask me any questions. If you don't have any questions, I'll see you in the next video. Aloha.